Okay, now in this second problem, we now have nitrogen flowing through a turbine. And so we now have a flowing type of system, an open system. We have nitrogen gas coming in at a pressure and a temperature. It has a velocity associated with it, so there will be some kinetic energy. And then it leaves, after expanding through the turbine, it leaves at a lower pressure, at a lower temperature, but a little bit higher velocity. So it picked up some kinetic energy as its specific volume changed, that type of thing. And the flow rate is 2 kilograms per second. Heat is being lost to the surroundings at a given temperature and at a given rate. And so we have heat leaving the system at a boundary temperature of 25 degrees C. And so we want to then determine the power output as well as the irreversibility. And again, we will have some irreversibility because of the heat transfer that is occurring and the entropy that's being generated during that process. Again, it's asked for the real gas model. And for the real gas model, for a flowing system, an open system, there is only one built-in model. There is not either a Lee-Kessler or a Nelson-Obert chart type of thing. There's just a single real gas model. And so the problem continues on as to what would be the power output if the mass flow rate was reduced in half. Now, the first thing that one would possibly think would be the case is that the power output would go down to half the value. But one has to be careful because not everything was cut in half. We still have this heat transfer at 100 kilowatts. And so things would only be reduced in half with the lowering mass flow rate if this heat transfer was also reduced to 50 kilowatts. And so if you wanted to do part C and put in your answers, you make sure that you realize that you still have heat transfer of a certain amount. Okay, so with that in mind, we now go to our test apps. We have now a flowing system. It is a single flow system. It is a turbine. It is a gas model. And we are going to now use the real gas relationships. And we then go to our HTML5. And so again, I was mistaken there. We do have the possibility of a Lee-Kessler or Nelson-Obert, and in this particular case, because it did not indicate which one, we'll go ahead and just use the Lee-Kessler. We will have a Nelson-Obert problem on the next problem. And so again, our working fluid is nitrogen gas. We are going to select the Lee-Kessler. And so what we know about this is that it comes in at 7 megapascals. So we can put in our value of pressure. It immediately, for nitrogen, figures out that the critical pressure for nitrogen is about 3.5 megapascals, and so our reduced pressure is about 206. We then can put in our temperature. In this case, the temperature was designated as being 500. And we see that it calculates it's about a reduced temperature of about 4, which means that the critical temperature is probably about 130 Kelvin. It's a cryogenic, nitrogen would be a cryogenic fluid at that, at very, very low temperatures. But in this case, we're at 500 Kelvin, and so we're fairly warm, if you want to think of it that way. We have, in this particular case, a flow rate of 2 kilograms per second. And so with this in mind, we have all of our values, we see that the compressibility factor, since we are quite removed from the dome because of the temperature and the pressure, our compressibility factor is only 2%. 1025, and so we're close to ideal behavior. If we were to do this problem with ideal gas, we would probably find very similar results. And so we have that information. We now can go to our second state, and as it goes through, oops, we forgot to add, in this case, there was a velocity associated with the fluid. And so just to watch here, here is our value, oops, okay, here's our value of flow energy, J1, 2079, or about 208. As I give it some kinetic energy of 100 meters per second, one sees that the flow energy went up by a small amount because of the kinetic energy component. So there's our state 1. Our state 2 is the same m dot, and it's nitrogen. Our kinetic energy is 150, and our pressure dropped to 1 megapascal, and so it's expanding through the turbine. We see that this 1 megapascal is below the critical point at that condition. Our temperature, as it expanded through, our temperature's at 300. And so we see that at that particular temperature, it is, again, above the critical temperature because we know this particular substance is cryogenic in nature, and so the dome would only appear at very low temperatures. And so we have our kinetic energy, we have our temperature and our pressure and our m dot, and we see in this particular case that it's very much or very close to behaving as an ideal gas. It's 0.997 for the compressibility factor. So once again, the same problem with nitrogen. If we had used ideal gas, we probably would find almost identical values of the answers. And so now we're ready to take this and go through the device panel. The device panel goes from state 1 to state 2. And now what we know is we know that the heat transfer occurs at 25 Celsius. And so that is the boundary temperature that our heat transfer is going in. And so this is incoming heat transfer to the tune, it's outgoing heat transfer. So it is a minus 100 kilowatts. And so heat is being lost to the surroundings at 100 kilowatts. And so there's our heat transfer. And so with that in mind, okay, we then have the information that we need for our calculating. So what we see then is the amount of work that was done is a positive 304 kilowatts. And so this is a turbine. It's producing work. And it's not producing as much work as it would if it had been adiabatic, but it is producing some work. And the other piece of information is the S dot gen in the entropy balance equation is equal to 0.427 kilowatts per Kelvin. Now in this problem, it's asking for the irreversibility. And so in this particular case, then we'll go ahead and do a super calculate, and we'll come over here and we'll say, okay, we want to calculate the irreversibility. And so we want to, first of all, look at the value of TB1, and TB1 was the temperature that the heat transfer occurs, in the boundary temperature. And so our irreversibility then is going to be equal to the value of that S dot gen. Okay, that was the S dot gen associated with the first device panel times TB1. And so that then gives us the irreversibility. Instead of units of kilowatts per Kelvin, it's now in kilowatts. And so it's 127.5 kilowatts is then our irreversibility associated with this particular process. Okay, just to highlight the irreversibility, I want to go back. I want to do a super calculate here, and I want to go back to the device panel. And what I want to show you in the device panel is the two values associated, in this particular case, the incoming entropy. And so this is entropy. We see that it's increasing, so we have state 2, and state 2 is the outgoing entropy. And so we do not have, in this particular case, we do not have the case where we have an isentropic process. Because of the heat transfer, we actually see that the entropy value is actually positive, or the entropy production is positive in this particular case. And again, it's due to the conditions associated with the turbine expansion, and it's also affected by either heat transfer in or heat transfer out. And so this is the TS diagram. Again, if one wanted to, one could have changed the scale down here by zooming out a little bit. And by zooming out, you can now see the two entropy values and the temperature process. And so, again, it's not an isentropic process, but rather one in which the entropy has been generated. Now, if I were to go to back to the device panel and look at this equation right here, what we have is we have an entropy generation, and that entropy generation is due to, because again, this is a balance of entropy, is due to heat transfer at a boundary temperature, and so we had a value associated with that. But also we had, because of the known two conditions of the in and the out, we also had this term here times the m dot. And so this value of Sgen is affected by the outlet and inlet conditions, the m dot, as well as the heat transfer rate. And so what I indicated before, if you were doing the what if question, what if the m dot changed down to a half of what the original, so instead of 2 it went down to 1 kilogram per second. The only way that you would have half of the S dot gen is if the heat transfer would have also been a half of the original. But, if you redid the problem, it doesn't say that. You would have then the minus 100 here times the temperature of the boundary. This term would be half as smaller, but then you would have you would not have half of the Sgen that then got multiplied by the boundary temperature.